All right, everybody, we're going to get rolling through, trying to get a little bit back on schedule here. Now for Major Danny Broyle. Dr. Clark Taylor for AFIT APNT.
All right. Well, thank you. I'm excited today to talk about this. This is a proposed project, something we'd like to add to ATAK, but it's not something that we have been working on yet. We've been working on related topics, which we'll talk about. So I'm Clark Taylor. Major Broyles is the one who had this idea. Captain Leland's my PhD student who's been working on some of these things. So that's sort of how we all fit together. So what's the motivation, what we're doing here? GPS is a great system. Here we talk about GNSS, that includes other people's satellite systems also. We can talk about pluses or minuses of that, probably not in this talk, but GPS works great, but particularly in urban environments, or if they're spoofing, you can have some significant problems. This is my very technical to scale diagram down here, but if you have a GPS satellite, let's see, do I have a mouse? Here we go. If I have this satellite up here and it's transmitting, especially when you're in urban areas, the assumptions behind GPS units is you're receiving all your signals directly. It's a line of sight, direct vector, right? When it bounces off a building, that means that you now have a longer time of flight going from the satellite to this receiver, and so then you end up with what can actually be very large errors, especially inside of urban environments. Like I say, spoofing is a whole other problem also. So what a lot of people have been looking at, and what we're proposing here, is also to look at the lower level GPS signals. So rather than just looking at it as a location position, right? Oh, this is your position and that's the measurement. We're looking at the individual signals that are coming from each satellite. And then also by pairing that together with both the inertial sensors that are in ATAK or other places, and also the baro sensor that's in the phones. Right? So there's been a lot of work in this area. This is just showing in 2016, Android actually opened up their interfaces so that you can get all of the low-level information off of GPS. So rather than just returning a lat long, you can actually get the specific pseudo ranges off of each individual satellite, and also there's this great thing called time difference carrier phase, which measures the actual velocity of the satellite with respect to you down to like centimeter per second precision. So it's amazingly accurate. So you can get all this raw data out of Android since 2016. In addition, Google has been running these smartphone decimeter challenges. They've done 3 of them. Probably the results of the 4th one will be released here in a couple months at the ION GNSS conference. And what Google is trying to do is get enough accuracy out of their phones to enable knowing which lane of traffic you're in when you're driving down a freeway, right? And so that if you get 10 meters worth of air in an urban environment, that puts you in the building next to you as opposed to on the correct road, right? But if you can get down to 1/10 of a meter, then I can tell you which lane of traffic I'm actually in. And so the competition, they went out and collected a lot of data, mainly all in the San Francisco area, so a fairly urban environment though. 3 different cell phones that they had, then they also had a very high quality GPS IMU unit, Novatel span unit for truth data, right? And they said, okay, how much, just by processing the data that you're getting out of the smartphones already, how accurate can I get, right? And just one of the papers, I'll be talking more about this. These are kind of the results they have. I don't want you to look at them too closely, except for this is sort of the traditional GPS. This is when they're out on sort of open roads. So here you're typically at, less than 5 meters very regularly. But by fusing everything together, you're able to get this much better red line down here. And when you're in urban areas, then you can see that your location errors are much larger traditionally, and we're able to get much better errors doing this. Right? So how do they get these results? This is using a technique called factor graph optimization. There's actually a math formula on here, I'm sorry. But the basic idea is you're fusing together lots of information from different types of sensors, right? If you have a Kalman filter, typically that has a graph that looks more like this up here, which this is over time, how do things happen? You've got dynamics, you've got different measurements. You turn this into a probabilistic modeling of the different sensors so you can fuse them all together. And the cool trick here is this is a very complex computationally approach. You can make it far more efficient by turning it into some sparse matrix things and be able to run things in real time. So what are the advantages of using factor graphs as opposed to other techniques? First off, you're doing batch optimization. So rather than just looking at one specific time, so this is the satellite signals I got at this instant in time, how do I optimize? I'm actually optimizing over basically as large of a time window as I want. You can kind of scale it. That's my last point here. You can kind of scale it to how much computation you have available or you want to use, right? If you have more computation, you can get more accuracy, use more time. There's also, I mean, after you're up to probably 15, 20 seconds of time, you're not actually getting too much more accuracy by adding more time, but there is a lot of advantage to using more than just the current instant, right? So it gives you better estimation backwards in time. It also makes your current estimate more accurate just because you're considering everything moving forward. Kind of the typical thing you might think of there is I got a GPS measurement at one time point and one at the next time point. If you can tie those two together with an inertial sensor, you can average both of them together, so it makes your current time more accurate, right? So you're able to do that. Also, when you're going over a batch of time, you get more accurate covariance estimates. With GPS, that's not as big of a deal. With Visionated now, where there's a lot of nonlinearities, factor graphs are much better at estimating covariance than sort of the traditional methods. But the factor graph is also advantageous over like a Kalman filter because it can handle multiple measurements of the same type. So inertial sensors pull you together over time. Time difference carrier phase from GPS also pulls you together over time, so you can consider multiple different types of sensors all in one thing. And it's also much better at rejecting outliers than sort of traditional methods that you just look at and say, oh, I'm doing this binary decision, right? So when Google ran this challenge, I specifically wanted to look at the method that came in. Well, they've run the challenge 3 times. The first 2 times he came in first. The second time he came in second. I think they're close enough that may even just be like random variability of the runs. But Taro Suzuki is a professor out of Japan, and this was his technique for solving the decimeter challenge, right? And so you can see this kind of complex factor graph on the right. But the reason why I'm focusing on his is he's actually released all this in open source. So you can go out there, you can download this code. He's got wrapper, so it all runs inside of MATLAB, and do all this great factor graph optimization. So what we'd like to do is take this open source work that Taro's been doing and apply it and actually get it running in real time on an Android phone. Right? We do have some experience doing this with, not with Android quality IMU sensors, but if you have sort of a tactical grade IMU, we've shown in our own work that you can get significantly better GPS results by fusing together in a factor graph the IMU and the GPS than you can with just GPS by itself, right? Where, you know, once again, it depends on the type of terrain. In the urban segment here, we went from, you know, sort of like 20, 30 meters worth of air from GPS down to about 2 meters worth of air, right? So that's our proposed idea, right? We want to take this open source factor graph optimization package that Taro's produced and integrate it into ATAK. And we want to do this in a way that is compliant with all of these sort of open source navigation topics, which I'll mention more about in a minute. But so, you know, first off, we can verify that we can do this on an Android with the existing data sets, you know, modify it so that it's not all in MATLAB, but it's actually in real time and running on an Android type of device. This is probably the type of thing we could do with a master's student with a little bit of funding. So this is sort of a proposed topic. Yeah, so let's talk about the open source. I like the last talk he mentioned both, you know, applying things on the mobile and the other platforms. The groups we've been working with both in the Army and the Air Force use a lot of these Aspen. So Aspen is the DoD. This is specific for navigation, right? These data formats, Aspen data formats are there. It specifies the data contents, you know, is this a pseudo range? What type of units is it in? Is it radians or degrees or meters per second or centimeters per second, right? So all this is specified in the Aspen data formats. We want to take all of the information that's coming out of the Android and make sure it's wrapped in Aspen compliant data formats. And that would also enable us, you know, to move across platforms and do a lot of things like the last talk was mentioning where, you know, how can I handle all these different platforms? The answer is yes if you're using Aspen, and then PNTOS also, which some of the things you were talking about there, the PNTOS is what's going on underneath the hood there. So if we can do this, you know, take the Android data that's being produced, all the GPS, make sure it's packaged in an Aspen compliant format, then we can plug it into PNTOS. PNTOS, we're also working on a different project in implementing that factor graph implementation into PNTOS. And if you want to go back to a Kalman filter or particle filter, PNTOS actually makes that very simple to sort of switch out which filtering algorithm you're using. So we can pull that together and really come out with a complete system. So that's sort of the low-level technical risk, I think, is, you know, let's take Taro's method, wrap it up into something that runs on Android, and make sure everything communicates with these DoD compliant standards, right? The North Star for TAK, the PNTOS, and the ASPEN. The second one is all the data that the Google Smartphone Challenge has been doing has been for vehicles. We'd like to make sure that we have some data sets that were for pedestrian data, make sure it works also for pedestrian data. And then there's a lot of great technical things that we could look at afterwards. One of the ones, especially if you're integrating with North Star, is making sure that we're getting accurate uncertainty estimates out of it. With GPS, that's fairly standard, but when you're starting to reject all these outliers, especially when you're doing these robust cost functions and scenes and factor graphs, I think truly understanding uncertainty in the covariance estimates that are coming out, so you could, North Star could do these comparisons of this approach versus that approach. Making sure we're producing accurate covariance estimates is a little bit harder technical problem, especially with most of the work that's been done before has been with high quality IMU sensors. So, if you're talking about a sensor that you're putting on a striker, for example, you can take the time to really characterize that sensor, make sure you understand it, and you know how these things are working. Android devices, I don't think that's possible. You just have to kind of assume it is what it is, and maybe you can kind of figure it out as you go along, right? So understanding that uncertainty and putting that together, and then especially if you start looking at spoofing scenarios, everything so far has been in urban environments, which is a challenging environment, right? But if you have somebody who's purposely trying to give you false GPS data, really getting the uncertainty with that would be a little bit harder. So that's what I have. I'll open it up for questions. I told them they gave me way too much time. I thought I had 15 minutes. I looked at the schedule, I had 30, so I'll put us back on time. So any questions, please?
Clark, you know that I think this is great work. Just want a little clarification. I think that North Star has integrated the relevant components of PNTOS from the Army.
I know they have done parts of that.
Okay.
So thank you. All right. Okay. I'll be around if people have other questions, so thank you.